Hi everyone, welcome to this GCSE Maths live group tutorial today on powers and roots. This is a higher level tutorial, so some more of the challenging stuff, and I can see lots of you have joined us before, so welcome back. I hope you guys had a really nice bank holiday break, and if you're new, welcome. This is a live group tutorial. It will go on for 1 hour, so finish at 1:15 today. And I'll be here. My name's Tilly, I work at my tutor. I'll be here throughout the session to answer any questions you might have, and you could just put those in the chat down at the bottom or in the Q&A as well, and we'll do our best to answer those. So as I said, today's session is on GCSE Maths, powers and roots, and today's session is run by Molly, who is one of our top maths tutors at my tutor. She's been with us for ages, completed lots of sessions with us, and she studies computer science and maths at University of Bath. And lots of you know her already because I can see you've been to lots of our past sessions. Just quickly before we start, had a couple of questions through about the GCSE English session today that didn't go ahead. Really sorry for that, guys. Unfortunately, it was just a technical problem that meant we couldn't run it today, which is really frustrating for us and you guys, but we will be making this up at another time, and just keep an eye on your emails for information on when that session will be run. We'll make sure to make that up for you guys really soon, and the issues that we had this morning are all fixed now, so everything should be running as usual from now on. So if we're all ready, then Molly, you good to start?
Yes.
Awesome. Have a good lesson, guys.
Okay, hi everybody. I'm Molly. You probably all know me by now. So yeah, today is on powers and roots. So we're going to start off by doing some stuff with powers, all of the laws of when you multiply things or add things, stuff like that. And then we'll do some work on roots, so surds. So all of that scary stuff like simplifying them, rationalizing the denominator and stuff like that. So hopefully it'll be a good session. Just whack any questions you have as we're going along in the chat. Some I might have to come back to at the end, but as we're going along, I'll try to answer as much as I can. So let's jump straight into powers. So indices, powers, the order of numbers, these are all words that mean the same thing. It's just multiplying stuff a certain number of times, as I'm sure you know. So, 2 cubed is 8 because it means 2 times 2 times 2. So this is the stuff that hopefully you're kind of familiar with, and we'll talk about what we can do with that basically. So let's start off just introducing some rules. So if we have, let's say 2 to the A, just say something like that, and we add something else, 2 to the B. There's nothing that we can do to simplify this when it's added. That's as much as we can do in terms of that. However, and that's the same for subtraction. However, if we were to do 2 to the A and times it by 2 to the B, that's the same as saying that that's 2 to the A plus B. So this is just a kind of rule to remember, and that's not just with 2. That works with any, we'll call this the base. This is the base, this is the power. So that works with any base, any power, if they're multiplied, and as long as these are the same base. So if we had 2 to the A times 3 to the B, we can't do anything with that. So they've got to be the same base and multiplied, and then we can smush them together. A really similar thing happens with division. You probably already know or kind of guessed. Let's say a different base, let's say 5. We have 5 to the X divided by 5 to the Y. That's the same as saying 5 to the X minus Y. We can see this, we can see some examples of this. So let's do it with 2. So let's say we have 2 squared times 2 cubed, that's like saying 4 times 8, which is 32. And this is the same as 2 to the 5, or 2 to the 2 plus 3. So hopefully you can see here, this is equal to this. That's what we've done there. So this can be super, super useful when we have things in terms of powers that we can simplify them down. Now, there's a couple of other rules which are a bit more complicated, but we can still work with them. So the first one is if we have a negative power. So let's say we have a to the minus 1. Now, all this means is 1 over a. So that means 2 to the minus 1 is a half, and 3 to the minus 1 is a third, and so on. The way that I always think about it is when you take minus 1 and put it on its side, it looks like this. This is like a minus 1, if you look at it. That's how I always remember that that's what that rule is. Okay, and then finally, fractions. And then with these, we're going to be able to simplify anything and work things out. So the final one is fractions. Now I'll say it in terms of algebra first. So this is going to be a to the power of 1 over b is the beef root of a. Now that looks a bit horrible. The one that you'll normally see is a half. So a to the half is root a. But we might also get a to the third. That's the cube root of a. There's a button for it on your calculator. There should be a button to do anything. And the cube root just means what do you have to cube to get it? Just like how the square root is the inverse of a square, the cube root is an inverse of a cubed. So using these, we can work out some really complicated indices. We can simplify them. So let's have a look. I've got some questions up here. We'll start off by just doing one like this that doesn't use any of those rules. So there are normally these kind of 2 distinct types of questions with indices. We've got ones like this that involve solving it algebraically. We just want to simplify. And we'll have ones where we've got horrible negative fractional powers and we've got to work out what the actual number is. So we'll go through both. So this here, there are a couple of ways that you can do this. It doesn't matter which order, because I think I've said it before, when we think about BODMAS, this bit here where it says, so it's brackets, order, or the indice, the power, division and multiplication, it doesn't mean do division first, then multiplication. It means do those two before you add and subtract. That's what that means. So it doesn't matter which way round we do this. So I'm going to do the, I'll do the division first. So this will be x to the 10 minus 7. So that's x to the 3 times x to the 3. Hopefully you can see that. I just simplified this and I got x to the 3. And then when I times it, we add them. So this becomes x to the 6. And you can see if I do it the other way and do the multiplication first, then I get x to the 13, that's 10 plus 3, over x to the 7, which is also x to the 6. So you can see whichever way round I do it, I get the same thing. All the questions that I'm going through today are from Maths Made Easy, that website. That's the one that I normally use. Okay, cool. Let's have a look at another. Let's have a quick look at this one. So 4x squared times 2x squared, all squared. So the first thing that I'm going to do here is work out this bit in the brackets, because that's what BODMAS tells me to do. That's also what my instinct kind of tells me to do here. So we've got to remember that when we're multiplying things, we multiply the numbers and we multiply the x's. So this becomes, the bit in the brackets, we know it's going to be something squared. We're just simplifying the bit in the brackets. 4 times 2 is 8. And x squared times x squared, well, that's x to the 2 times x to the 2. So it's x to the 2 plus 2. So this is 8x to the 4. hopefully you can see that. Oh, I just realized there's a rule that I forgot to go to, which we're going to come to here. The rule is, let me just quickly note it down. If you have a to the x and then to the power y, you multiply those powers. So this is a to the, this is a to the xy. Realize I forgot to say that. So if you have 3 to the power of 4, and then you square that, that's 3 to the power of 8. So if they're multiplied, you add them. If it's to the power again, you multiply them. Cool, so that helps us here. Now again, when we're doing something squared, we have to do each element. So our 8 and our x to the 4. So we do 8 squared, and we do x to the 4 squared. So 4 times 2, that's 8. So here's what we get, 64x to the 8. Yeah, perfect. Well done. I'm not actually sure what level all of these are. Some of the surd stuff that I'm going to be going through will go right up to level 8 or 9. This indices stuff is probably year 10. I'm not 100% sure. Okay, so that's how we do that one, just step by step. Oh yeah, this is an interesting thing to go through as well. These ones. So this first one, the point that this is getting across, gosh, there are a lot of rules that I clearly forgot existed. Small little things that you don't think about once you're really used to them. So anything to the power of 0 is 1. It doesn't matter what that thing is, unless that thing is 0. 0 to the power of 0 gets very confusing. If you're a nerd like me and that interests you, go and read about it. Mathematicians actually disagree on what 0 to the power 0 is. So yeah, anything else to the power 0 is 1. So 2 to the power 0 is 1. Minus 47 to the power 0 is 1. And also 1 to the power of anything is 1. Because if you have 1 and you multiply it by itself, however many times, it's always still 1. Similarly, 0 to the power anything is 0. Because if you take 0 and you multiply it by itself loads of times, you're going to get 0. So what do I think about 0 to the power 0? Good question. I'd probably cop out and say undefined. But it is a really interesting read. Okay, let's have a look at some these here. Which shall we go for? Let's have a look at one like this. So, sometimes you have to do a tiny little bit of simplifying before you can even tackle the question. So, when we have a fraction squared, just like how when we multiply, we square each bit, here we square the top, square the bottom. So I much prefer making things a top-heavy fraction rather than a mixed fraction. So that's what I'm going to start off by doing. I'll show you both ways, actually. Yeah, because it will make it. I'll kind of show you. So, oops, need to get rid of that. There we go. So, first way, making it a mixed fraction first, 2 4/5 into a mixed fraction. Well, we do our 2 times 5 is 10 and add that on the top. So we get 14 over 5 squared. And then we just square the top and square the bottom. So that gives us 196 over 25. That's 14 squared. I'd recommend knowing squares up to about 15 squared, just because when it comes to square rooting and stuff in surds questions, which we'll come to in a bit, and ones like this, if you have something to the power of a half, it's really useful if you can spot straight away that that's 14 squared. Just useful. So that's that. And then if we did it without, let's have a look. So without actually might be harder than it's worth, because if we think about what this is 2 plus 4/5, right? That's what 2 4/5 means. So when we square that, we'd have to do our FOIL technique. So we'd have to do like 2 times 2 plus 2 times 4/5 plus 2 times 4/5. So it gets quite confusing. So I'd strongly, strongly recommend converting to a top-heavy fraction first. Hopefully that makes sense. Cool. Let's have a look at, yeah, let's do this one. 25 to the power of minus a half. So this is the first one that we've got, which I'd say is kind of the higher level question of powers. But there's a really neat trick. So what we're going to do is we're just going to split this up. So I'll show you what I mean. So this is the same thing as saying 25 to the power of half times minus 1. That's what minus a half is, right? It's a half times minus 1. Now we're going to do the reverse of what we did before. So do you remember when things were to the power and then to the power, they got multiplied? So if we kind of reverse that, we know that this is the same as 25 to the half to the minus 1. Because if we work backwards, well, we know that to the power just multiplies these. And now we can work out this inside the brackets and then do it to a power. And I'll show you both ways, because you could write this another way as well. So what this gives you, 25 to a half. We remember our rules. Half meant square root. So the square root of 25, and we always take the positive root. That's a convention with indices. Because you know 25, the square root is plus or minus 5, but we take the positive one. So this is 5 to the power of minus 1. And then do you remember minus 1? Like I said, turn it on its side, it becomes 1 over. So this is 1 over 5. So 25 to the power of minus a half is a fifth. I think that's pretty cool because this as an expression doesn't really make any sense. We have no idea what that means, but it's just a fifth. Now, the other thing that we could have done is said, I only chose it this way round because I felt like it. We could also have said that this is 25 to the power of minus 1 to the half. Just putting these two the other way round. That's totally allowed. So then what we'll do is we'll work out this bit in the brackets first. So that's 1 over 25. Remember, minus 1 is 1 over. And then that's to the half. And then exactly the same as when we raised it to the power of 2. If we're doing this, then this means that we square root the top and square root the bottom. Root 1 is just 1. Root 25 is 5. So we get the same thing. So it's just preference, whichever way around you do it. It doesn't matter at all. Cool. I hope that makes sense. We'll have a look at some others as well. Right, it's quite confusing. Let's have a look at this one. Now, I'd say that this is pretty much the hardest one of the hardest indices questions that you can get. So 64 to the minus 2/3. Now, the reason that this is really hard is because we've got a minus in there and we've got a 2/3. So that's kind of a weird thing to think about. But what we're going to do, we're going to split it up just the same. So this is 64 to the minus 1 times 1/3 times 2. Hopefully you can see where I've got that from. So you can try doing this in reverse. Minus 1 times 1/3 is minus 1/3 times 2 is minus 2/3. I've just split it up into elements because we only ever want a minus 1. We only ever want a fraction with a 1 on the top because those we know what to do with. So we're splitting it up. So then we do our kind of reverse thing and stack these powers. So this is where order is quite important. We could start with 64 squared, but I personally do not want to do 64 squared. Normally, the best way to do it is with the fraction first. Helps if I'm actually writing. So we'll do 64 to the 3rd. And normally the minus 1 last, like I said, it doesn't matter. Just here, I don't want to do 64 squared, so I'm going to do this to the 3rd first, then squared, then minus 1. So hopefully you can see that this is exactly the same as this. all I've done at the moment is just split it up to the third squared to the -1. Just shout if that doesn't make any sense, because this is the main kind of thing here. And now that we've done that, that's the hard work done. We just break this down and do it step by step. So 64 to the third, now that means the cube root of 64. So you can do it on your calculator, or we recognize the small cube roots. Again, I'd recommend learning cube roots up to maybe just up to 5. And hopefully you can see that this is going to be 4, because 4 times 4 is 16, times 4 is 64. So 4 cubed is 64, which means that the cube root of 64 is 4. So now we have 4 squared to the -1. And then we do it again. We're going to do this next middle bit. So 4 squared, that's 16. And that to the -1. -1 is 1 over 16. So what we found here is that 64 to the -2/3, which is, I don't know, that's just a crazy indices to me. We're only really used to seeing squared, cubed, stuff like that. Now we've got minus and like a negative fraction, but it's just the same thing as a 16. That's a good question. People are asking whether this would be calculator or non-calculator. Probably non-calculator. And the reason is because calculator papers, they usually save questions that you have to have a calculator for, like trigonometry. That's the only example I can think of. Formulas where you have to, like iteration and stuff. Whereas this, we haven't needed a calculator for anything that we've done so far, because they're never going to be, trust me, the more questions you do, you're really going to recognize your squares and your cubes, because they always use the same numbers. They'll always start with 64 or 49, it's a square, or 81 or something like that. Okay. There's just one more type of question that I want to cover, and then we'll go on to surds. Okay. I don't actually have a question for this, but it just came to me that I want to cover it. So, okay. So let's say we have a question that says, simplify 2 to the power of 4, or not even simplify, let's make one that we can actually work out. So 2 to the power of 4 times 4 to the power, no, okay, I know what I want. I want to do a solve for x question, sorry, right. This is what happens when I suddenly realize I want to do a question. 2 to the power of, let's say 2x plus 3 is equal to 8 to the power of x minus 1. I'm hoping that this works. I think it will. So this looks horrible, right? Suddenly we've got an equation and we've got an x in there. But all we need to do is make sure that these bases are the same. Because if these bases are the same, then we can equate the top bits. I'll show you what I mean. So the trick here, the kind of sneaky thing to notice, is that 8 is 2 cubed. So that means that we can write this side as 2 cubed to the power of x minus 1. Does that make sense? All I've done there is I've replaced 8 with 2 cubed. And then if you remember by our rules of indices, this is 3 times x minus 1, because it's to the power, we multiply them. So this is 2 lots of 3 x minus 1. I've just multiplied them here. And now look at this. This is equal to this. 2 to the 2x plus 3 is the same as 2 to the 3 lots of x minus 1. Well, if they're both 2 to the power of something, then the powers must be equal. If 2 to the power of x is the same as 2 to the power of 4, x must be 4. Hopefully that's quite intuitive. And now, suddenly, powers are completely out of the equation, and we just set these things equal. And we can just solve this and say 2x plus 3 equals 3x minus 3. I've just expanded that out there. Then I'm going to add 3 to both sides. 2x plus 6 equals 3x. And then subtract 2x, so 6 equals x. So x equals 6. And if you don't believe me, try it on your calculator. What you'll see, so if you try 2, substitute 6 in here, 2 to the power of 15, it's going to be equal to 8 to the power of 5. So try it if you don't believe me, but hopefully that makes sense. This and the previous one that we did are the hardest indices questions that I think I've ever seen. And hopefully you'll see that they're not too bad. So even if you get really hard ones, you can still work with it and work it out. I'll do one more, I think I'll do one more like the previous one, and then we'll go on to surds. So I'll just do one more where it's like to a negative fraction or something. So let's do, hang on, just got to work something out. Okay, let's do 32 to the minus 3/5. Okay, now again, this looks horrible. We seem to have kind of, I don't know, I still can't get my head around this indice. Maybe you don't think it's as cool as I do, maybe I'm just a nerd. But minus 3/5 seems like a really weird thing to raise the power to. You know, it's something that, I don't know, I can't picture it. But we can actually evaluate this to a really nice number. So hopefully you can remember as before, we're going to split this up. So to the power of minus 1 times 3/5, but we only want that 1/5. Remember, if we have a fraction, we want a 1 on the top. So this is minus 1 times 1/5 times 3. So hopefully you can see that that's how we split this up. We take the minus 1 out, we take the 3 out. Because we always just want a minus 1, not a minus anything else. And we always just want a fraction with a 1 on the top. And then again, we're going to put this in the nicest order, which goes fraction, number, negative. That's what I would recommend anyway. Because the thing is, if we do it another way around, if we start with the minus 1, we then have to work with a fraction for the whole thing. If we start with the number, we have to work with a huge number for the whole thing. So I'd always, yeah, I think that this way just works the nicest. So, fraction, number, negative. And hopefully you can see that this is exactly the same as this. By that law that when we do things to the power, it's multiplied. And these multiplied is the same as this. And then we'll just do it step by step. So 32 to the power of 5th is the 5th root of 32. And again, these are ones that are really good to memorize, is powers of 2. So if you see anything like 2, 4, 8, 16, 32, 64, 128, you know, all of those, if you just keep multiplying by 2. So it's a really good thing to know that 2 to the power of 5 is 32. And you can always work it out if you get confused. Normally, if it's a big root, if it's like the 5th root, it's normally going to be 2. So we have 2, 4, 8, 16, 32, 5th root. So this is 2 cubed to the minus 1. And suddenly this looks a lot nicer. No big number, no fraction. So 2 cubed, that's 8. Put that minus 1 on. And 8 to the minus 1 is 1 over 1/8. So we've got this horrible random number to a horrible negative fraction, and we end up with something quite nice. Yeah, brilliant. Loads of people got that as well. So well done. Okay, great. If you're still confused about anything, want me to go over anything else, pop it in the chat or in the Q&A and I'll come back to it at the end. But I want to make sure that I get surds done as well. So that's what I'll go through. Cool. So, first thing is that all a surd means is a root, basically. So root 2, root 3. That's a surd. It's a horrible word that I think kind of gets thrown around sometimes without being explained. but it's not a scary thing. That's all it means. And the reason that these two topics are together is because it's the inverse of squaring something. So that's why, just like we put multiplication and division together, we put addition and subtraction, they're inverses. So square and square root are also inverses. They reverse each other. So we've got some, just like we had some rules about powers, we've got some rules about roots as well. And we're just going to be working with square roots. You don't have to work with anything more in terms of these. So here are our rules. If you have root AB, then we can split this up. So A and B here, that's A times B. We can split this up into root A times root B. You can break apart this root. So if you have root 6, that's the same as root 2 times root 3. And I think that's pretty cool because, yeah, these numbers are irrational and yet we can still do some weird kind of equating. Yes, I'm going to cover rationalizing the denominator. That will be the main part of this bit. Then similarly, if we've got a root A over B, that's the same as root A over root B. So we've got these really nice things that we can, do here. Cool. If we have root A times root A, that's just A. So that's because we can combine these and make it, why is that pen so big? And make it root A squared. Remember, by this rule here. And like I said, because they're inverses, if you root something that you've just squared, you get the same thing. So root 2 times root 2 is just 2, for example. I think these are all the rules that you're going to need. Goodness knows I'll probably come across one. And just a quick note about working with surds. If in doubt, treat it, imagine that you were dealing with an x, right? So let's say we have 2 root 5 plus 3 root 5. That looks like a strange kind of thing, right? But let's imagine, say this was 2x plus 3x. Well, we wouldn't hesitate in calling that 5x. So that's the same thing, but here the x is just root 5. So you just add them like normal. They're just a variable in their own right. They're just a thing. You know, they're just, we could call it 2 orange plus 3 orange, and that's going to be 5 orange. That was just what was near me. It's just a number. Or like pi. If you had 2 pi plus 3 pi, it would be 5 pi. It's just a way of representing a number. So hopefully that makes sense. So that's why we can do stuff like this. Okay. Let's jump in to some questions. So the first type, and I guess the most simple type, is just simplifying a root. So let's say we had something like root 75. We can write this in a much simpler form. The trick is that we're going to try to work out what this, what multiplies to make 75, where one of the two things is a square. And you'll see why in a moment. So I can see that 25 goes into this. So 75 is 25 times 3. So we'll write it as that. So all I've done here is I've just written 75 is 25 times 3. I'm allowed to do that. No one's stopping me. That's just a different way of writing 75. Then we're going to use our rule that we just covered and split this up. So this is root 25 times root 3. So far, all I've done is just written 75 a bit differently and then split it up. Yeah. Now, this is why we wanted one of them to be a square, because root 25 is a whole number. Brilliant. Root 25 is 5. So we can write that. 5 times root 3. And then mathematicians don't like writing times, so we would always just express this as 5 root 3. And hey presto, root 75 is the same thing as 5 lots of root 3, which I think is pretty cool, that these two irrational numbers are linked like that. So hopefully that makes sense. I'll go over another, I think I'll just go over one more example. So let's say we have root, what should we do? Root 63. So again, our trick is always to write this in terms of something that is a square times something else. So here, and again, you will get good at spotting these, I promise. Root 75, if you do lots of practice questions, you'll see it more than once. You'll start to see the same ones coming up again and again. So we can write this as 9 times 7. Again, that's just another way of writing 63, is 9 times 7. Then we use our surd rule. So that this is root 9 times root 7. And then root 9 is just 3, because that's why we chose 9, because it's a square. We could have written this as 3 times 21, but it wouldn't have helped us, because neither of those are square, so then we'd just be stuck with root 3, root 21. Whereas if we write it like this, we can write it as 3 root 7. So hopefully that makes sense. And again, hopefully this will make sense more as we go through, because we've got 10 minutes before questions, and I'll go on to rationalizing the denominator now. So this is probably the main topic in surds and the one that a lot of people seem to hate. Rationalizing the denominator. First of all, I'm going to explain to you what this means, because these are just words, right? What this means, so an irrational number is one that can't be written as a fraction. So such as root 2, that's irrational, because if you put that into your calculator, you're going to get 1.14, what, I can't remember exactly what it is, but a really long decimal, right? That doesn't stop. And it doesn't stop, which means that you can't write it as a fraction. Pi is an irrational number. And any square root, unless it's like the square root of a square number, like root 4 or something. So basically any kind of normal surd is going to be irrational. So root 3, root 5, root 7, all of these, they're irrational. So what we want to do, what rationalizing the denominator means is if we have something like 1 over root 2, mathematicians hate having irrational numbers on the bottom. So we want to rationalize the denominator. We don't care if the number on the top is irrational. That's fine, doesn't bother us. But we don't like the number on the bottom being irrational. That's because it makes it quite difficult to combine them and stuff. And also quite difficult to think about. So you know my favorite way of thinking about fractions is in terms of cake. If we have an irrational fraction of cake, that's fine. We can kind of visualize that. I mean, we can't because that would be a fraction, but we can kind of think about if we take root 2 of a cake, you know? However, we can't really think of a cake that is root 2. Hopefully that makes sense. Maybe it doesn't. Just know that mathematicians hate having irrational numbers on the denominator. And seeing as we're all mathematicians, you should hate it too. So we want to get rid of it. So the way that we get rid of it, when it's just something like this, well, we know that if we times that bottom by root 2, we'll get 2 out. So why not do that? So if we times this by root 2 over root 2, this is perfectly allowed because root 2 over root 2 is just 1. You're allowed to times a fraction by 1 and it stays exactly the same. And then what we do here is when we multiply fractions, we do the tops and we do the bottoms. So 1 times root 2 is just root 2. Root 2 times root 2 is 2. That was one of our rules at the beginning. And this is a form that we like. This is nicer. So if you don't believe me, try putting them in your calculator, 1 over root 2 and root 2 over 2. And you'll see that they give you exactly the same thing. Some people are complaining about why I said, like, why do they hate it? It's because it makes them harder to work with. And hopefully, if I get on to some harder questions involving these, which I think I should do, you'll kind of see why. Let me just see if there's one on here that I can go through, because that would make it a lot nicer. Oh, I don't think this is what I want. It's the kind of questions where you have to simplify things. Once we've rationalized the denominator, it becomes a lot easier to work with, basically. If there isn't one on here, I will try to come up with a question, but it might go wrong. So, okay. Okay, I'm going to go over this one. Now, I don't know if you saw when I opened that document, this is a level 8/9 question. But I think everyone watching this can get it. It might take you coming back and rewatching the video, bombarding me with questions, go for it. But this isn't too bad, I promise. So, first of all, examiners love to word questions in horrible ways. So show that it can be written as k root a. That's just saying simplify it as much as you can, it will come out in this form. So 5 root 3 or 2 root 7 or something, right? So what we're going to do is we're going to simplify each bit. I'm going to start with this part first. In fact, I'm going to start even more specific. I'm just going to start with this bit, this root 300 over 4. Now, root 300 over 4. If you remember from the beginning, one of the rules, we can split this into root 300 over root 4. There's a couple of ways that we can do this, actually. I'm not sure which way I want to do it. I'll show you both. And root 4 is just 2. So this is root 300 over 2. And then we can simplify down root 300 in a similar way. The other thing that we could have done is 300 divided by 4 is 75. So we can write this as root 75. And I told you it would come up again. This is one of the ones that we did at the beginning, if you remember. So if we remember, this gives us 25 times 3. So root 25 times root 3, so 5 root 3. And what you'll see here is that if we take root 300, we can split this into root 100 times 3, which is root 100 times root 3, which is 10 root 3. So then this becomes 10 root 3 over 2, which is 5 root 3. Just dividing that, I'll write that out. I'm aware that sometimes I say things and don't explain them. So root 300 is 10 root 3. So 10 root 3 over 2, that's 5 root 3. Just dividing it by 2. Basically, do either of these ways. This looks really complicated, but you can just do this blue method, basically. Make a root 75, and we can simplify that to 5 root 3. Hopefully that makes sense. Cool. Now let's look at the whole of this left part here. So 4 root 3 times that. So 4 root 3, 4 over 3. So we've just rewritten root 300 over 4 as 5 root 3. And we know that when we multiply a fraction, we just multiply it by the top bit. That's one of our rules of fractions that we've covered before. And when we do 4 times 5 root 3, again, imagine what you would do if this was 4 times 5x. You'd have no problem in calling that 20x, right? So it's the same thing. This is 20 root 3 on the top, and keep that 3 on the bottom. Hopefully that makes sense. Just give me a shout if that doesn't make sense, but this is just fraction multiplication. So that wasn't too bad. That's just what we've done, right? Now let's have a look at what our expression is. It's 20 over 3 root 3. Now we haven't done anything to this right half That's plus 10 over root 3. Now, here's what I mean. This is why mathematicians hate having these on the denominator. Wouldn't it be lovely if we could combine these in some way? Now, to combine them, we want to have the same denominator, right? But it's like, what do we times 3 by to get root 3? Well, we don't. We root it. So I think it's kind of a... Hopefully that makes sense. Wouldn't it be so much nicer if we had root 3 on the top and some number on the bottom? Because if it was numbers on the bottom, we can do what we know and love and make our denominators the same to add these fractions. So that's why we don't like having a root 3 on the bottom. I really hope that makes sense. That's why mathematicians don't like it. It's because we can't combine lovely things like this. So what we can do now, let's just have a look at this. Well, let's get rid of that root 3 by timesing the bottom by root 3, which means we also have to times the top by root 3. Whenever we're rationalising the denominator, you think of, well, what do we want to times the bottom by? Let's times the top by that as well. So then this becomes 10 root 3 over 3. And now, look what this has become. 20 root 3 over 3 plus 10 root 3 over 3. We can add those just like we would normal fractions. Because they both have the same denominator, we can just add the tops. And remember, if this was 20x plus 10x, what would it be? 30x. So it's just 30 root 3. It's no different just because they're surds. So this is 30 root 3 over 3. Now we can simplify this even more because the 3 goes into the 30 here. These are multiplied. So we're allowed to do that, divide the top and the bottom by 3. And we get, which a couple of you have already got and put on there, 10 root 3. That's our final solution. So that looks like, it looks like more working out than it actually was because I was really explaining every step and a lot of them in a couple of ways. So it's not as much work as I've written there. But how cool is it that we can get this horrible expression just into 10 root 3? The 4 thirds at the start, we multiplied here. Someone just asked about that. And to make this 20 root 3 over 3. Now, I'm aware that I'm going into question time. So if there are any questions, let me know. If not, what I'm going to go over is more complicated rationalising the denominator, which is probably what you want to go over anyway. But yeah, are there any questions?
Yeah, cool. Molly, how about we move on to that, and guys, pop your questions in the chat now, just because there are very few questions. If most of them are
okay.
Yeah, we can go through at the end.
Cool. Perfect. Okay, let me grab one here. Oh my gosh. Let's do this. So this is probably one that you're maybe more familiar with. I'm not sure. One like this where it says rationalize the denominator of this. So I kind of think that this looks horrible to look at, right? We don't know what this really means. And it's not like we can just multiply this by root 5, because then we'd have 3 root 5 plus 5. And that's just as bad. We've still got something there. So what we're going to do is we want to multiply the top and bottom by something that's going to get rid of the root 5 from the bottom. And what we're going to do here is basically use the difference of 2 squares. So I'll show you what I mean. If we take this 3 plus root 5 and times it by 3 minus root 5, so you might recognize this as a difference of 2 squares. Like if you have x plus 2, x minus 2, right? That gets rid of the x term because we get 3 times 3. And then basically, this is the key bit. We have 3 root 5 minus 3 root 5. So that kind of quashes that root 5 term. If you're not following yet, don't worry. We'll work through the question. Just accept it for now. Just do it because, you know, it's what I promise you it works. So we're going to multiply the top and the bottom of this by 3 minus root 5. basically, if you want something just to remember, whack a minus sign in the middle of that. Or if it's already a minus, make it a plus, right? You want to do this. And then we can work this out. So this is going to be 1 plus root 5, 3 minus root 5, over 3 plus root 5, 3 minus root 5. So let's think about the top first. Let's think about the numerator. We've got 1 plus, that was a weird way of writing it, 1 plus root 5 times 3 minus root 5. Now, this we're just going to do by the FOIL method, like we did when we covered quadratics. We're just going to make sure that we multiply each element by every other element. So we see 1 times 3, that's 3. So that's front, outer. 1 times minus root 5, that's minus root 5. 1 times it is just itself. 3 times 5 from that middle two, 3 times root 5. So that's plus 3 root 5. And then root 5 times minus root 5. Well, we know that root 5 times root 5 is 5. Remember, that was one of our rules. And then that's just a negative. So it's minus 5. So that's our numerator. And we can actually simplify that more. Let's combine our numerical terms and our surd terms. So 3 minus 5, that's minus 2. And minus root 5 plus 3 root 5, that's plus 2 root 5. If you don't get that, have another think. Just imagine that they're x's again. I always encourage you to do that. Minus x plus 3x, that's 2x. Just like this is 2 root 5. And then the denominator here, 3 plus root 5, 3 minus root 5. Well, like I said, these root 5 terms are going to cancel out. So we get 3 times 3, which is 9. And then I'll write them down. We get a plus 3 root 5 minus 3 root 5. And then again on the end, we've actually got the same thing, plus root 5 times minus root 5. So that's again a minus 5. And these terms cancel out. If you add something and then immediately take it away, it's 0, they cancel out. So our denominator is actually just 9 minus 5, which is 4. So now let's whack them together again. We've got our numerator, minus 2 plus 2 root 5, and our denominator, 4. We can actually simplify this a little bit, lucky us. We can divide every element by 2. If you remember, this is how we can simplify fractions. If every element, so everything that's on the top that's added, everything on the bottom that's added, we can divide by 2. So this becomes minus 1 plus root 5 over 2. And that is our solution. So the key step to remember from that is that we multiply it by whatever's on the bottom, kind of almost like the opposite of that, whatever it is, so that you've got something plus something, something minus something. That's the key thing to remember. And then all we've done here is just use the FOIL method to expand out both and simplify it. Yeah, hopefully that makes sense. Are there any more questions?
Hey Molly, a couple of people are asking some general questions about sort of revision and things. Someone asking, do you know any websites specifically for OCR exams?
No, is the short answer. I'm not 100% sure. Normally, if you Google like maths GCSE OCR questions, a lot of good links come up. So give that a go, but I don't know any specific ones, I'm afraid.
Brilliant, thank you. And someone's asked, I don't know if this is possible, Molly, but could you show us what links you click on the Maths Made Easy website to get the
Yes, I'll show you exactly what I do since I'm sharing my screen. So I literally just so say I was looking for these surds ones. I always start GCSE Maths. You can see all the ones that have come up. Surd questions. It will pretty much always be the first link that comes up. Anything that's mathsmadeeasy.co.uk. So go on that. Oh, in fact, that was the right one. And then here's the Maths Made Easy website. And then the worksheets that I use, if we scroll down here and look here, the example questions are sometimes quite good. They kind of walk you through one. Oops. Oh my gosh. My computer wants to work. So the example questions are like this. Oh my God, the first one's root 75. I didn't even know that. Sorry, it comes up all the time. And then they show you the answer and show you actually step by step. And then this is what I use here. So the worksheets and exam questions. So this is the one that I've been going through. Surds hard. So well done if you followed. But they've got loads of different levels and they've got mark scheme as well. So it's a great website. I'll put the link to this one actually on the Zoom chat in case you want to look at this now.
Great, thank you. And just had a response actually from a couple of you guys saying Save My Exams is good for OCR because it has some of the content that's relevant there. So thank you for that. Molly, that was just a question. Sorry if this has been answered, but on the last question you were going over, someone's asked, why do you have to change the signs?
Let me just go back into it. Why do you have to change this? I don't know where. Oh, I see what you mean. Why do you have to change the signs here? It's because we want to multiply it by something that's going to cancel out the root on the bottom. And when we do it with instead of a plus, a minus, we get this here, this 3 root 5 minus 3 root 5, which cancels out that root 5 completely. And you see we've ended up with something that doesn't have any root 5 on the bottom. I think if you go on to that Maths Made Easy and have a go at some more rationalizing the denominator questions using this method, even if at the beginning you don't understand why, just use this method. And I promise that as you do more questions, you'll see why you're doing it. It will make more sense because you'll see time and time again, oh, those cancel out, that's why. So hopefully that makes a bit of sense as to why we do it.
Great, that's all the questions I can see, guys, unless anyone in the last sort of minute wants to pop anything in there. Molly, could you quickly go back to the third rule page?
Yes, gosh, if I know where this one.
Brilliant, thanks. And just a reminder, guys, if you sort of throughout the session are wanting to make notes of things or find that you want to go back to something, the session has been recorded, so you can access it on the My Tutor YouTube channel later today. And you can just, if you want, rewatch the entire thing and keep sort of going over the bits that you wanted to go a bit slower on. Let's just have a look. Brilliant. I think because we've got only a couple of minutes left. Molly, someone's asked, oh, sorry, the question's gone. How strange. Someone's asked, will there be a catch-up English session for the one that was missed today? Yes, there will. We're not 100% sure when that one will be, but we'll let you know via email. And is biology still on today? Yes, biology is still on today. Today we have GCSE physics in 45 minutes at 2, and then GCSE biology at 3:15. So hopefully see lots of you in that session. Brilliant. I think we'll wrap up there if that's okay, guys. Thank you so much, Molly. That was a great session. Guys, hopefully see you later today, or if not, in our next math session. So thanks and bye.
Thank you, everybody. Hope it made sense.
Bye.